Hey guys, in this video I want to show you an interesting probabilistic phenomenon related to coin tossing. So what we're going to do in particular is imagine that we are flipping a coin some large number of times, and we're going to inspect some proportions and some numbers of the heads that we observe and see what different behavior we see. So the first thing we're going to do is import numpy as np, and then I'll also make some visualizations, so I'll import matplotlib.pyplot as plt. So I'm just going to make some large number of coin tosses, and I'll also make a sort of vectorized trial representation, so we'll do 100 trials. This is going to be a really simple simulation, so it's cheap to do that. N. So this is going to generate random numbers between 0 and 1, all independent of each other, and the number of random variables will be the number of trials times the number of flips that we're doing, which is n. From here I want to compute a cumulative sum of the number of heads that I observe. So to do that I can do np.cumSum, and then I'll do a comparison x greater than 0.5, and then I'm going to sum along the first the second axis, because Python is 0 indexed, to obtain a rolling count of the number of heads that I observe. So to see that this works, let's just run this in interactive mode. I did save it, and here is z, and you can see that this is indeed a count, and it's a pretty large matrix that we've constructed here. So the first thing that I want to do is visualize the convergent behavior of the proportion of heads relative to what we'd expect. So this is an unbiased coin, so in a large number of trials we'd expect to see about 50% of the coins turning up heads. So let's visualize that. Do if true, plt.figure. I'm going to create another variable here called r equals np.array, and this is just going to be a vector that is the number of flips that I've done. And then I want it to be based 1 so that we avoid a division by 0 error, so I'm going to add 1. And then I'll do plt.plot. I'm going to plot r versus z divided by r minus 0.5. And I think I have to transpose it in order to get the dimensions to line up. I'm going to set the alpha equal to 0.05, add a grid, and then show the plot. So what this is it's the sort of excess proportion of heads over what we'd expect, and what we'd expect is 50%. So if we now run this, I'm going to turn off interactive mode. We do indeed see some very nice behavior and convergence, where all of these lines representing a rolling proportion seem to converge to 0, which means that the excess is 0, or that the proportion of heads is 0.5. Makes sense, and this is what we'd expect. Now, on the basis of this, one might expect that the number of heads is also going to be, or the excess number of heads will also be convergent in this way. That is to say, if we flip 100 coins, then we might expect the excess number of heads to converge to 0. So in other words, the deviation from 50 will get smaller and smaller. And let's see if that's true. So in order to implement that formula, we just need to move the r variable over to the 0.5. So this is saying number of heads minus the expected number of heads, so that we can compute the deviation from that value. And now let's see what happens when we visualize this. As you can see, this is not a convergent quantity. In fact, it appears to disperse, which I think is very interesting. Now, why does this happen? Well, I think it has to do with the fact that what we're basically looking at here, this z variable, is a binomially distributed quantity. So a binomial distribution with probability of success 0.5. Maybe I'll write that down. So I think that this is a binomial random variable with p equals 0.5 and n equals some number. Now, if we know about binomially distributed random variables, we know that the variance is going to be increasing like n times p times 1 minus p, otherwise known as n, in this case, n over 4, since p is 0.5. Therefore, the variance of this quantity is actually increasing in the number of coin flips that we do, which is why we don't see the convergent behavior that we see in the first visualization. Let's look at that again. Let's go back. Well, actually, we'll visualize both. How about that? Here's the first plot. This is basically an average, and so you can see it converge to the expected value. That might be by the law of large numbers. And here's the second plot. This is not an average, and you can see that it diverges. And I think the variance of this is going to be n over 4. Alright, thank you guys for watching. I hope you enjoyed this video, and I hope it explained an interesting probabilistic phenomenon to you relating to coin flips. And if you liked the video, be sure to comment and subscribe, and I'll see you guys in the next one. Bye.